Welcome to Chapter 4 of the Introduction to Nanomaterials series. This is where things get exciting. After learning what nanomaterials are, how to make them, and how to characterize them, we now explore why they're so remarkable. At the nanoscale, materials exhibit properties that don't exist in their bulk form. Gold nanoparticles appear red instead of gold. Magnetic particles lose their permanent magnetization. Catalysts become orders of magnitude more active. In this chapter, we'll understand the physics behind these phenomena and see how they enable revolutionary applications. Size-dependent properties arise from two fundamental effects we discussed earlier: quantum confinement and surface effects. Optical properties change dramatically at the nanoscale. Metal nanoparticles exhibit localized surface plasmon resonance, where light causes collective electron oscillation at specific frequencies. Semiconductor quantum dots have size-tunable bandgaps from quantum confinement. Magnetic properties transform when particles become single domains. Below a critical size, thermal energy can flip the magnetization direction, leading to superparamagnetism with zero remnants. Catalytic properties enhance because smaller particles have higher surface-to-volume ratios, exposing more active sites. Structure-sensitive reactions particularly benefit from low-coordinated corner and edge atoms. Thermal properties change because phonon mean-free paths become limited by boundaries at small scales. Let's explore each of these in detail. When light interacts with metal nanoparticles smaller than its wavelength, something remarkable happens. The electric field of light drives the conduction electrons into collective oscillation. Think of it like pushing a child on a swing. If you push at the natural frequency, the oscillation amplitude grows large. For metal nanoparticles, this resonance condition depends on the particle's size, shape, composition, and the surrounding medium. At resonance, the particles strongly absorb and scatter light, creating the beautiful colors we associate with colloidal metals. The local electric field near the particle surface becomes enormously enhanced, sometimes by factors of 100 or more. This enhancement is the basis for surface-enhanced Raman spectroscopy, where molecules near nanoparticles give amplified signals. The physics is described by my theory, which calculates the extinction cross-section from the particle's dielectric function and geometry. Gold nanoparticles are the classic example of LSPR. While bulk gold has its familiar yellow color, gold nanoparticles can appear pink, red, purple, or even blue depending on their size. Small particles, around 5 nanometers, have LSPR peaks near 520 nanometers and appear pink or light red. As size increases to 40 nanometers, the peak red shifts toward 550 nanometers, and solutions appear deeper red to purple. Larger particles and aggregates shift further into the red or even infrared. The peak also broadens with increasing size due to radiative damping. The surrounding medium strongly affects LSPR. Higher refractive index media like glass shift the resonance to longer wavelengths compared to water or air. This sensitivity to the local environment is what makes gold nanoparticles excellent sensors. When molecules bind to the surface, they change the local refractive index, shifting the LSPR peak. We can detect this shift spectroscopically. Plasmonic sensing exploits the sensitivity of LSPR to the local environment. When target molecules bind to functionalized gold nanoparticles, the local refractive index increases, redshifting the plasmon resonance. The shift is proportional to the change in refractive index. Delta lambda equals m times delta n, where m is the bulk refractive index sensitivity, typically on the order of 50 to 100 nanometers per refractive index unit for gold nanospheres, and higher for rods and shells. Real-time monitoring is possible by tracking the LSPR wavelength continuously. A binding event appears as a rising signal, and subsequent washing shows dissociation kinetics. This provides both thermodynamic and kinetic information about molecular interactions. The key advantages are label-free detection, since no fluorescent or radioactive tags are needed, real-time monitoring of binding events, and high sensitivity down to picomolar or even femtomolar concentrations for some systems. Applications span glucose monitoring for diabetes, DNA and protein detection for diagnostics, and environmental pollutant detection. Quantum dots exhibit size-tunable photoluminescence through quantum confinement. When a photon is absorbed, an electron is excited from the valence band to the conduction band, leaving behind a hole. This electron-hole pair, called an exciton, is spatially confined within the nanocrystal. After rapid relaxation to the band edges, the electron and hole recombine, emitting a photon. The band gap, and thus the emission wavelength, depends on particle size. Smaller particles have larger band gaps and emit higher energy, bluer light. Larger particles have smaller band gaps and emit lower energy, redder light. Key advantages of quantum dots include high quantum yield, up to 90% for well-passivated core shell structures. The emission is narrow, with full width at half maximum of only 20 to 40 nanometers, compared to 50 to 100 nanometers for organic dyes. Quantum dots are much more photostable, resisting bleaching under continuous excitation. And they can be excited by any wavelength shorter than their emission, unlike dyes with narrow absorption. The Bruce equation quantifies the size-dependent band gap. It has three terms: the bulk band gap, a positive confinement term that increases as size decreases, and a negative Coulomb term for electron hole attraction. The confinement term dominates, so the effective band gap always increases for smaller particles. Different materials have different bulk band gaps and effective masses, giving different size-color relationships. Cadmium selenide covers the visible spectrum with sizes from about 2 to 7 nanometers, emitting from blue to red. Indium phosphide offers similar coverage with a heavy metal-free composition. Lead sulfide and other narrow-gap materials extend into the infrared. For CDC, a practical calibration shows 2-nanometer dots emit around 450 nanometers in the blue, 4-nanometer dots emit around 550 nanometers in the green, and 6-nanometer dots emit around 620 nanometers in the orange-red. This precise size-color relationship is why synthesis control is so critical for quantum dot applications. Bulk ferromagnetic materials contain multiple magnetic domains separated by domain walls. The domains have different magnetization directions, minimizing the total magnetic energy. When magnetized by an external field, domain walls move and domains align, creating net magnetization that persists when the field is removed. This is what makes permanent magnets permanent. At the nanoscale, things change dramatically. Below a critical size, on the order of several tens of nanometers for iron oxide, particles become single domain because the energy cost of creating a domain wall exceeds the benefit. Single domain particles have uniform magnetization throughout. But here's the key insight. If the particle is small enough, thermal energy can flip the magnetization direction over the anisotropy energy barrier. The magnetization fluctuates randomly, averaging to zero in the absence of a field. This is superparamagnetism. In an applied field, the moments align, giving strong magnetization. When the field is removed, thermal fluctuations randomize the moments again, leaving zero remnants. This is why superparamagnetic particles show no hysteresis. The blocking temperature, T sub B, is the temperature below which a superparamagnetic particle appears ferromagnetic on the measurement timescale. It's given by the equation T sub B equals K times V divided by K sub B times the natural log of tau sub m over tau sub 0. Here, K is the magnetic anisotropy constant, a material property. V is the particle volume, which depends on diameter cubed. Tau sub m is the measurement time, typically 100 seconds for DC magnetization. Tau sub 0 is the attempt time for magnetization reversal, about 10 to the minus 9 seconds. The key insight is that blocking temperature scales with volume, so larger particles have higher blocking temperatures. For practical applications at room temperature, you want T sub B well below 300 Kelvin. For magnetite, this means particles smaller than about 25 nanometers. Cobalt ferrite, with higher anisotropy, has a smaller critical size around 10 nanometers. The choice of material and size determines whether your particles will be superparamagnetic at the operating temperature. Superparamagnetic iron oxide nanoparticles, or SBIONs, have numerous biomedical applications. In MRI, SBIONs serve as T2 contrast agents. Their large magnetic moments disturb the local field, accelerating the relaxation of nearby water protons. This darkens the signal in T2 weighted images, providing negative contrast. SBIONs can be functionalized to target specific tissues or tumors. Magnetic hyperthermia uses alternating magnetic fields to heat magnetic nanoparticles. As the field oscillates, superparamagnetic particles dissipate energy through Néel relaxation, generating heat. If particles accumulate in tumors, this localized heating can kill cancer cells while sparing surrounding tissue. Targeted drug delivery uses external magnetic fields to guide drug-loaded magnetic nanoparticles to specific locations in the body. The drugs can be released by stimuli like pH change or temperature. For all biomedical applications, superparamagnetism is essential. If particles retained permanent magnetization, they would aggregate in the bloodstream. Iron oxide is particularly attractive because it's already FDA approved for some applications and relatively biocompatible. Catalysis occurs at surfaces, so the fraction of atoms at the surface directly affects activity. As we saw in Chapter 1, the surface-to-volume ratio increases dramatically at the nanoscale. For cubic dihedral clusters, which approximate real nanoparticle shapes, the surface fraction drops from 100% for a single atom to about 92% for a 13-atom cluster, 76% for 55 atoms, and 52% for 309 atoms. Below 10 nanometers, a substantial fraction of atoms are at the surface. Why does this matter? Surface atoms are catalytically active because they have unsatisfied coordination bonds that can interact with reactant molecules. Bulk atoms are fully coordinated and essentially inert. This geometric effect alone predicts that smaller particles should be better catalysts per unit mass. But there's more. Not all surface atoms are equal. Corner atoms have a coordination number of about 5, edge atoms about 7, and face atoms 8 to 9, compared to 12 for bulk atoms. Lower coordination means higher reactivity. This leads to structure sensitivity in catalysis. Structure-sensitive reactions are those where the turnover frequency depends on particle size. This happens when reactions specifically require low-coordinated sites like corners and edges. The fraction of corner atoms decreases rapidly with increasing size because corner count is fixed at 12 for cubic dihedra, while total surface atoms grow as size squared. For a 2-nanometer particle, corners are only a few % of the surface atoms, and for a 10-nanometer particle, the fraction falls well below 1%. If a reaction specifically requires corner sites, the turnover frequency drops dramatically as particles grow. Classic examples include co-oxidation on gold nanoparticles, where catalytic activity appears only below about 5 nanometers and increases steeply at smaller sizes. Bulk gold is inert. The low-coordinated sites on small gold particles can adsorb and activate Co and oxygen. Structure-insensitive reactions, in contrast, proceed with similar rates on any surface site. For these, the total surface area matters but site distribution doesn't. Many hydrogenation reactions fall into this category. Mass activity measures catalytic performance per unit mass of expensive metal, critical for practical catalyst design. It combines surface-specific activity, or turnover frequency, with metal dispersion, the fraction of atoms at the surface. For structure-sensitive reactions, there's an optimum size that balances competing effects. Very small particles have high surface fraction, but may be too small for optimal electronic structure or may bind reactants too strongly. Very large particles have low surface fraction and waste expensive metal in the inactive bulk. The optimum often falls around 2 to 5 nanometers. For platinum in fuel cell oxygen reduction, particles around 3 nanometers show peak mass activity. Smaller particles bind oxygen too strongly, larger particles have insufficient surface. Cost drives this optimization in practice. Platinum is among the most expensive industrial metals, so minimizing loading while maintaining performance is essential. Nanoparticle catalysts achieve much higher mass activity than bulk metal, enabling practical fuel cells and catalytic converters. Thermal conductivity in crystalline materials is carried primarily by phonons, quantized lattice vibrations. In bulk materials, phonons travel with a mean free path that can be hundreds of nanometers or more before scattering. When structural features become smaller than this mean free path, boundaries scatter phonons and reduce thermal conductivity. This is called boundary scattering. A simple scaling argument gives thermal conductivity as roughly the bulk value times d divided by d plus the phonon mean free path. When the characteristic dimension d is much larger than the mean free path, you recover bulk conductivity. When d is comparable to or smaller than the mean free path, conductivity drops significantly. Silicon nanowires, for example, can have thermal conductivity reduced by a factor of 100 compared to bulk silicon. This is actually useful for thermoelectric devices. Good thermoelectrics need low thermal conductivity to maintain temperature differences, combined with high electrical conductivity. Nanostructuring reduces phonon transport while preserving electron transport, improving thermoelectric efficiency. Let's summarize the key size-dependent properties we've explored. Metal nanoparticles exhibit localized surface plasmon resonance, where collective electron oscillation creates strong, size-dependent light absorption. Gold nanoparticles change from pink to red to purple as size increases. This enables plasmonic sensing and photothermal therapy. Quantum dots have size-tunable emission from quantum confinement. The Bruce equation predicts bandgap increases as size decreases. Smaller dots emit blue, larger emit red. This enables QLED displays and multiplexed biological imaging. Magnetic nanoparticles become superparamagnetic below a critical size when thermal energy can flip magnetization over the anisotropy barrier. The blocking temperature equation predicts this transition. Superparamagnetism is essential for biomedical applications like MRI contrast and magnetic hyperthermia. Catalytic activity enhances at the nanoscale due to high surface fraction and abundant low-coordinated sites. Structure-sensitive reactions show particularly strong size effects. Thermal conductivity decreases when boundaries scatter phonons, useful for thermoelectrics. In Chapter 5, we'll see how these properties enable applications in electronics, medicine, energy, and how AI is accelerating nanomaterial discovery. See you there.